simple ones. And this weight update is governed by terms which I'll introduce called the learning rate, which is how much each time the weights are up, how much of the weights are used to update, so how much the error is used to update the weights, and the momentum term, which is term how much were they changed in the last cycle and how much of that is retained in this cycle. So I'll talk about those more. So this is our neural network. We have our input layer. These are our inputs. We usually linearly scale the values between -1 and +1 or 0 and 1. We have our hidden layer, mathematical feature detection layer. We have our output there, which we might descale the predictions back from 0 to 1 back to a number. The inputs are fed in. They are scaled. They are passed through the weights, which are randomized initially. And then those values are summed. So input times weight 1, input 1 times weight 1, input 1 times weight 1, plus input 2 times weight 2, plus input 3 times weight 3. Sorry. So that summed set of values passes into the... So we're taking the input from this, times it by that, summing it, taking the input from this, times it by that, summing it, taking the input from this, times it by that, well, it's summing it. So they're all added up. Those values are then passed into what we call the activation function, or transfer function. So in this case, it's a sigmoid, an S-shaped curve. So if the sum of the weighted values is very low, it will be down here, produce a weak signal. If some of the weighted values are here, it will produce a strong signal. That is called the activation energy. So the values are fed in, they produce an output. Those values are then passed through another layer, multiplied by the weights, summed, and then we pass them to the output layer, make a prediction. So that's our first feed forward part of the neural network. The actual values, so the predicted values are then compared to the ground truth, the actual values. And we get a delta value, a difference. Yeah. This is why this algorithm is sometimes called delta algorithm, delta rule. Historically, that's a long time ago. So that difference is then fed back through the network, and as you see, these weights are updated. And then it's fed back another level, the previous bit of the network, and those weights are updated. So we have had our first cycle through, where one case is presented, the weights have been updated. The model prediction has been made, the error has been tested. So we have a new state of our neural network. We then feed the next value in, it goes through the new weights, through the new summed values, a prediction is made, and those are then back propagated through. So we keep going through cycles, feed forward, back propagation. And when every individual in the population has been considered, we have completed one. So we keep cycling around, feeding forward, back propagating, making predictions. And the error keeps dropping, hopefully. And in this way, we are learning a solution to the model. So you can see now how through training, some of those weights are very weak, some of those weights are very strong. And through reinforcement of the model, those weights are made stronger and stronger if it keeps seeing the same patterns. So what's more than likely happening is this input is pretty closely correlated to the question. In the first case, it sees a pattern and says, yes, that's a good part of the yes-no answer. The second case, third case, fourth case, fifth case, sixth case, keeps seeing the same thing, each time reinforcing those weights. Whereas this bit, the network, maybe it sees it in 1 in 20 cases, 1 in 50 cases. So it's a very weak signal. So the pattern is not strong enough. So the weights are not updated. So in this way, as you can see, through feed-forward and back propagation, the model is learning patterns and building. So if we were to look at this in terms of a classifier, we've got in this model, well, 2 hidden nodes, but in reality, the one I'm showing is 3. So essentially what we're doing, stitching together 3 sigmoid functions, because each one of our hidden nodes has a sigmoid function. This model would be 2, because there's 2 hidden nodes, so it would confuse you. But this model had 3, let's say. So by stitching together a number of hidden nodes, a number of sigmoids, where the number of sigmoids is the number of hidden nodes in the model, we can build a decision that separates out one group from another. So that's what we're doing. We're classifying, building a decision boundary, using the neural network to define that decision boundary. Just to reiterate, this is how we did it. So an important aspect of any machine learning algorithm, particularly neural networks, is what's called the hyperparameters. These are the parameters of the network or the algorithm that define how it will learn. So we have the parameters, which are our genes, proteins, whatever. Our hyperparameters are things like learning rate, momentum, number of hidden nodes, loss function, transfer function, and so on. Now, often algorithms have many hyperparameters. Neural networks, with all the different approaches that are used, neural networks can have hundreds or even thousands of hyperparameters. That gives a lot of flexibility, but it requires a lot of optimization. You've got to search through all those hyperparameters. You've got to find the best solution, or find an approximation to the best solution. So what we sometimes do is a process called hyperparameter tuning. We make lots of models with different architectures, different structures, and see which model gives us the best performance. Now, there are new strategies, new approaches coming out all the time, particularly for deep learning and neural networks, because they're kind of a popular subject within the network. But we have to beware. There's a lot of hype around some things. So something can be the best thing at the moment, because a lot of people believe it to be so, but then suddenly something new comes out and it's not. So things like, we used to get a lot of competition between data scientists at conferences where somebody had spent 20 years optimizing their model for a standardized data set. And they were proudly saying, I've got 88% performance on this data set with my classifier that I've developed over the last 20 years. The next person to present was a PhD student. They'd been working for 8 months and they got 92%. So we have to be careful about what is the best method and overhype the method. So it's good to try lots of things. We also have one hyperparameter is the activation function. So this is the bit that goes in the middle of the neural network, the functionality that's it's based on. So some weighted values, input times weight, is applied to this one. And that gives an activation energy for the node, an output for the hidden node. And we can have many functions. So we can have a straight line linear function. Sorry, we can have a sigmoid function, which is quite good for biological problems. Biology tends to follow these sort of curvilinear distributions. Transformed, it gives you a kind of a Gaussian curve, or a normal distribution curve in some ways. We also have a favourite of mine, which is actually quite good. It's a hyperbolic tangent. This has more linearity built into it. It still has some of the characteristics of a sigmoid S-shaped curve. More popular recently, and also quite popular for deep learning, for convolutional neural networks, is ReLU, a rectified linear unit, which has a firing. So it does nothing until it reaches a certain value, with a linear output, which has, in some cases, limitations. We have a leaky rectified linear unit as well, which is an advancement on that, which has some negative bits. And then we have something called squish, which has a linear part, then has a non-linear part at a lower level. So these are all things that can be tried out as transfer functions or activation functions in the real world. In reality, start with one, see how it goes. If it does badly, try another one. Have some comparisons. There are other things which are important, so the loss function. This tells us performance based upon, and gives measures of how well the model is doing. Most of these are suited to classifiers. So, for example, the error function or loss function, we can use mean squared error. How often did it get it right and wrong? How wrong did it get it right? What's the first ground truth as a squared value? That's quite good. That's been around for many years. That's the common method. There's also, though, we can use a likelihood loss. So basically, this is a more probabilistic view of getting it right or wrong. How many times does it get it right? How many times does it get it wrong? So it multiplies the predicted probabilities for each example. We have a hinge loss, which is used in SVM, and this is the distance between the classes, the maximal distance between the classes and the line. I'll show more about that in a bit. And we have cross-entropy loss. So this is often used, it's a measure of entropy. So entropy is kind of noise, randomness. So it's measuring the difference between the probability distribution of a model and what it estimates the true distribution from the actual result. So is there a shift in the distribution of the values? We have divergence loss, which is callback-Leibler divergence loss function, which calculates how much information is lost when we approximate one distribution with another. So how much information is lost from the prediction to what actually happened. And then we have methods for regression. We have mean absolute error loss. So this takes the root of mean squared error and combines the errors on an unsigned basis. And then we have quantile loss. So that looks at distribution of quantiles along the predicted value and says how often did it get it right within the quantile. It's a way of kind of fudging the error a bit into buckets along the continuum. You do lose some potential performance. Now, we can also look at weight initialization strategies. So we can We always randomize the weights of the neural network. Now we can change the weight distribution. We can set them all as positives, 0 to 1. We can set them between -1 and +1, or -0.1 and +0.1. So we can follow a normalized distribution. We can constrain the weights, so we use a smaller standard deviation of weights, so randomized between term numbers. We can precede the weights. So say we've trained a model before, we know those weights have worked. We can precede the model with the trained weights to reinforce a particular hypothesis or bias. Not always ideal at the outset, but if you've got a strong opinion that something should be in there, then you can, because of previous evidence, you can do that. You can also take the weights from a previous model. If you've been saved, you bring them in, that model might work, but then you can then retrain the new model with those existing weights and see the input, the new data. So I'm coming to the end of what we're going to do today. There is a challenge, and this is about learning rate and momentum. So data exists with these complex distributions. You can imagine a surface with the potential errors of prediction of a neural network. And that surface has got peaks, it's got troughs, it's got deep bits, less deep bits. And you can imagine a ball that's rolling around that surface trying to find the lowest point. So that's the solution is the lowest point. So that's the global minimum. So we've got a 2D representation of that. So we have a local minima where the error is higher, a global minima down here. And our goal is to train the model so that the error drops and drops and drops. It doesn't get constrained in the local minima, it goes over that like the maxima, and then it gets to the global minima. So we're trying to get that ball to roll to the lowest point of the hill through the training of the model. So the problem is, during training, models can get stuck in local minima. We don't want that to happen because the error of the model will be greater. It's not as good as it can be. So we have to develop a strategy in order to solve that problem. The other thing is, the more noisy, more complicated our data is, so you can have multiple local minima, you might have multiple solution states to the problem, all of which are very good. So, it becomes a challenge. You have to find a strategy to get over these local maxima, get into global minima. So with respect to learning rate, the model is training as it proceeds. I've talked about these epochs that go round and round and round, the error drops. Learning rate is the amount of error used to update the weights. So if we have a learning rate of 1, all of the error is used to update the weights. If we have a learning rate of 0.1, 10% of the error is used to update the weights. So it's learning and feeding back. This is the amount of weight or error it feeds back. So if there's a high learning rate, it'll train very quickly. But that's not always a good thing, because you see what's happening here. We've got a high learning rate. It's jumping over the local minima. It jumps on very big, but then it's missing the global minima. So it's overshot it, and it just keeps oscillating backwards and forwards over the global minima, never reaching an optimal solution. So the learning rate, if it's too big, won't reach the global solution. If we can use a lower learning rate, we use a smaller amount of the error, then it makes smaller jumps, and it gets to that global minimum. It just takes longer. It's more equal. Now, what some people do, because they don't want models to take a long time, is they start off with the learning rate big and then have a function which lowers the learning rate as they go on. So it makes big leaps at the beginning, but as it starts to train, so that learning rate starts to get smaller. So they achieve the global minimum bigger, and then smaller and smaller and smaller steps. Because if you're looking at lots and lots of models, you want it to run quickly. You don't want each model to take a month to train. So you use a strategy like that. So learning rate, how much of the area is used. We have to make some decisions about how we select that learning rate, or we can automate it. You know, we can use strategies to automate the hyperparameters through hyperparameter tuning. Okay, so this is the other solution. This is the momentum solution. So doing gradient descent, algorithms get stuck. The momentum term ensures that this doesn't happen. So it means that the ball has a speed and a weight and it keeps going. It's like, you know, imagine it rolling, going over the hill, rolling further, going over the hill. So momentum, what it does, it uses some of the previous changes in weight to keep that ball rolling. So it doesn't just feed the learning rate back, it also feeds a bit of the weight change from the previous epochs back as well. So if we have a low momentum, what happens, you can see the area drops and drops, but then because the momentum is low, it just kind of gets stuck in the local minimum, goes backwards and forwards and then stops there. It's lost its momentum. If, however, we have a higher momentum, it then has the energy to take it over that local maximum to the global minimum. So we have a higher momentum, a lower learning rate, generally speaking, and that means that we can get to a solution that's more effective. So that's all I'm going to cover today. I'll move on to this, carry on with this lecture tomorrow. I don't want to keep you here for another quarter of an hour. We'll stop. It's now just from 5. But before we go, do you have any questions? Think about what you've heard. We will be releasing these notes after the event. If you think of something, have any questions overnight, please ask me tomorrow. Okay. Great. Thank you very much.
Thank you.
Okay, so the point I'm making That's great, thank you. So the point I'm making is, in many situations, and the software will show you, all of these have been implemented. So while it's useful to have a rough idea of the theory, you don't have to be able to have the exact technical detail to implement one from scratch. So knowing about what these different techniques are and how they work is useful, but you don't have to have a comprehensive knowledge in order to use them. It's a bit like, as I say, if you drive a car, there's the skill in driving the car, but you don't have to build your car before you drive it. So it's knowing the techniques, but what I'm going to show you is ways to start using them as well, so that they can empower you to start using those things and start discovering new things. does anybody have any questions? Has anything occurred to anybody overnight? Is there anything you want clarifying? And this is an opportunity for you to do that. I can go over things again, explain things again. Please ask questions.
I'm new in this AI thing. So if I have a data set and I'm not aware of much of its features, like I have a very limited set, but I want to extract some more new features which are unknown to me. So is it possible to do?
This causing an issue with this one. I mean, we can just... Okay, yeah. So you want to find out, you've got a data set and you want to find out new features of importance about that data set. Yeah, so, but you have, it's a high-dimensional data set or it has a large number of variables, you just don't know how they relate to the thing of importance. Yeah, so I can show you some more of that, and I will show some more of that coming up. But essentially the method we use is we look at each feature on its own in the first instance across the data set. We look at its ability to model an answer to a question. So say you have disease healthy and you've got all these variables. We test variable 1 against disease healthy, see how good it is at predicting it. We then test variable 2, see how good it is to predict it. Test variable 3. So in this way, we're testing out every single variable in the list, and we can rank them and see which are the best ones to use. In that way, we can start to see at a first pass what is important. What we can also do though is we can start building in a stepwise fashion models. So we could say, right, what's the best single variable? Okay, we find the best single variable, we keep that. We then add remaining variables to that to find the best pair of variables. So
like that, by selecting variables which are significant according to our data, we can add it on in a model based on this.
Yeah, so we're adding things into the model to build the model up in a stepwise fashion based upon performance. So we start off with find the best single one, then the best pair, the best triplet, the best quadruplet, and so on. And keep growing the model until we stop getting an improvement in performance. So that's another way of building up a model from these data sets. Some of the methods I showed you yesterday around weights and things like that, they have limitations for these big data sets, so I wouldn't use those. But that was just to illustrate historical stuff. Any other questions? No.
Could you please explain the activation function?
Sure. So, activation function is a function which is the mathematical basis of the neural network. So this piece here is the activation function. So what it is, it's once we have the summed values, so we have this value multiplied by the weight, plus this value multiplied by the weight, plus this value multiplied by the weight, and then we sum that value. We'll get a value from that. And then we apply it to the activation function. So what that does is, okay, let's have a look at our value of the sum of the weights across here. Okay, so it's quite high. So just reading effectively off the graph. So the amount of activation is, if it's high, goes out as high. Okay. So the number that comes from this sum is passed on to this function. So if, for example, it's very low, then the output's low. If it's high, the output's high. So it's transforming that number onto an S-shaped curve. And that dictates what comes out of that node into the next layer. So, if we look at these activation functions, here, if the value's low, the value's low, and it would just linearly relate. So that's a linear activation function. That has the potential to go to infinity and the potential to go to minus infinity. If you look at a sigmoid, it tends to 0, it tends to 1. So it's dampening down those high ends, which is good, because sometimes the model will run out of control. So if it's low, let's say it's minus 6, we get a value of 0. If it's minus 2, we get a value of about 0.1. If it's plus 4, we get a value of 0.99. If it's plus 6, we get a value of 1. So the number comes in, the activation function, that value goes out. Yeah? So where it starts to have an impact as well are with rectified linear units. So this is about a decision-making process. So here, let's say we have a value of minus 5 coming out of that hidden node. Nothing happens, we just get 0. And we get 0 at minus 4, 0 at minus 3, 0 at minus 2, 0 at minus 1, 0 at 0. And then, only when it's positive does it start to go up. So that's immediately squashing that distribution to get rid of all the negatives. So what we're doing then is choosing these activation functions based upon how they modulate what's coming into them from the network. And then by using different functions, we can start to represent different characteristics of the patterns in the data. Yeah, there's nothing stopping us having multiple hidden layers as well. So we could have a hidden layer which is full of sigmoids, then have a hidden layer full of rows. That would have a particular effect on the network, but we could try that out if we wanted to say that. There's no right or wrong answer. It's for, we don't normally say, oh, this is this sort of data, we're going to use 3 layers of a row and 1 layer of a sigmoid. It's a trial and error approach as to which ones we use. What we tend to find though is 10H and sigmoid work better for biological systems because there's more of that noise. It's not such a crisp cut-off as in physics systems, which would be more useful for ReLU or in some cases linear. So it's just really how the numbers are transformed. Any other questions? I'm presuming we can start. I don't know if it's streaming. I'll carry on anyway. So the next method is an alternative machine learning method. It's in the public domain. It's been used quite a lot. And that's support vector machines. A support vector machine is a supervised approach, so we're telling it the ground truth. So is it this class or that class? We can generally only cope with 2 classes. And it doesn't make support vector machines will not make a continuous regression type analysis. So what it's trying to do is find that decision boundary. So if you remember yesterday I talked about decision boundaries. You have a cloud of data, the decision boundary is the thing that separates one group from the other through multidimensional space. So this technique is reliant on a kernel. A kernel is kind of a seed function. So it's a type of function class. So kernels are a weighted function which maps the decision boundary. So it's a bit like how I showed yesterday where the neural network maps the decision boundary by putting three sigmoids together. A kernel will use a function that does a similar sort of thing. So a signal picture machine will use a kernel that does a similar sort of thing. And we can choose what type of function. So sometimes it might be a linear function, so that's where there's a straight line decision boundary between the groups. We can use a sigmoid, we can use a log, or we can use a radial basis function. So radial basis functions are quite interesting. They're contracting and expanding spheres. So what that's trying to do is creating a sphere, or a couple of spheres, which are trying to define the classes. And it's the radial basis, so the radial is effectively the width, or half the width of the circle, half the diameter of the circle. And what happens is the SVM changes the weights of the function, effectively scaling the data through the multiple dimensions to maximize the distance between the points and the decision boundary. So it knows the distance from class A to the line, it knows the distance from class B to the line, and then it moves the line such that the distance between A and the line and B and the line is as big as possible. So what does that look like? Well, it's back to this just 2D plot of the population. What we have effectively is healthy, we have disease. And what we're trying to do is separate out one from the other with this line. So the first thing we do is we map the distance between each point in the population and the line. So we know the red lines have so much distance away from the line. These will be negatively weighted because they're on the wrong side of the line. And then we have the greens which have so much distance from the line. So we're mapping out that data space and the line's position relative. That effectively wasn't explained by the first rule. So that would look like this. So we take the X1 group, we split that into a pure cancer class, and we split it into a mixed class. Okay? And then we have our third rule, and now we're looking at the y-axis, and we're now saying, and it's the feet of these people that we take as the point where they, in the space where they exist. So we're now saying if less than y1, then it's a cancer class, and if greater than y1, it's a healthy class. So with three nested rules, we've explained that whole population. So that's using a logical structure in the tree. Now broadly, if you look at this, you can see we have got effectively a decision boundary, which is sort of a little bit sigmoidal in its nature. So now we have a classifier. We can say, well, we put our cases through this decision tree and they get filtered out into particular groups. And what that looks like is something like this. So we take X1, our rule there, take X2, our rule there, take Y1, our rule there, and we have a way of classifying into the three, into the two types. The problem is, like everything else, this now is probably overfitted. It's a small population, it won't generalize well. So in the same way with a neural network, we have effectively mixed up the data into different groups. We can do this with a decision tree as well. So what we do is we take lots of trees, and what do we have when we have lots of trees? We have a forest. So a random forest is taking lots of splits of the data and then creating a tree for each. So these all look the same in reality, they won't, but what we have in fact is multiple trees, each one is a different randomized view of the data. And by running it through that, we get a better more generalized approach, more generalized model. So we don't get overfitting. So any questions on that so far? Okay, so there's a few other things we need to consider. And this is where we get into gardening and arboriculture. So, first of all, a tree can be very complicated. You could have, theoretically, as many branches in the tree as you have individuals. So this is a branch for this individual, this is a branch for this individual, and those branches get very complicated. So we can prune the tree to make it more generalized. We effectively take branches out and put them back into one amalgamated group, which may not be perfect, but it will do reasonably well. It will be more generalizable. So we can start taking out branches. We can effectively look at consensus across the random forest. We can merge trees into kind of one amalgamated tree, and we can have partial decisions on branches as well. I'm not going to go too much into that because that gets a bit more complicated. Suffice it to say, random forests are a pretty good classifier. They work quite well. They can work well for relatively high dimensional data, and we've seen some similar performances in random forests to neural networks. It's an alternative tool. So that's the end of that lecture on the introduction to machine learning. I think